Okay class, welcome back. Today we are going to venture into the exciting world of balancing redox reactions. I'm going to just give you a heads up that we are in for a wild ride today when it comes to balancing these types of reactions. I will say once you understand how these methods work and when to use them, it is not a terribly hard thing to do, but it can be intimidating at first. My objective for you is that you'll be able to balance redox reactions by the end of this lecture. In saying that, let's jump into our lecture. Chemical equations must be balanced to show correct quantities of reactants and products. Sometimes balancing these equations can be a little bit more complicated and less straightforward than what we have worked in the past. Let's take the reaction of copper and nitric acid. So we write copper S or CuS plus HNO3 aqueous as our reactants. You might originally think this is a single replacement reaction since we are given an individual element and a compound. But the sad truth is stuff is seldomly as easy in chemistry. In this reaction we produced actually three products. Our products produced are CuNO3 or copper 2 nitrate, aqueous, plus NO2 gas, plus H2O liquid. Note that oxygen only occurs in one place in the reactant side but three places in our product side. This can make our redox reaction particularly hard to balance. For the rest of this video, we are going to see the different ways in which we can use to balance these redox reactions. The first method we're going to talk about is by oxidation numbers. This method is based on balancing the total oxidation number of both sides of the equation. Before we work a problem through this method, though, let me give you the steps we are utilizing for this method. Our first step is to assign oxidation numbers to all chemical elements in the equation. Our second step is to identify atoms or ions that are oxidized or reduced. In other words, the oxidation number is changed. Third, we determine the change in oxidation numbers for the atoms or ions that are oxidized and for the atoms or ions that are reduced. In other words, we quantify it. Step 4 is that we make changes to the oxidation numbers to equal the magnitude by adjusting the coefficients in the equation. Finally, step 5 is to use conventional methods to balance the remainder of the equation. Now let's balance our copper and our nitric acid equation. First step is to assign oxidation numbers to each element. Copper by itself has an oxidation of 0. Oxygen oxidation in nitric acid is -2. We have 3 of them, so for a total of -6. Hydrogen is always a +1 unless it is paired with a metal, so to cancel out the oxidation and make the compound neutral, nitrogen must have an oxidation of +5. Now let's look at our product side of the reaction. Copper's oxidation is +2, and oxygen's oxidation is -2, and nitrogen once again is +5. In NO2, oxygen's oxidation is a -2, and we have 2 of them for a total of -4. In order to cancel out our nitrogen oxidation, we need the number to be a +4. Finally, we can see in our water where hydrogen's oxidation is +1, we have 2 of them, so our oxidation for oxygen must be -2 to cancel out. Now that we have to identify the changes in atoms and ions, whether or not they go through oxidation or reduction. Looking at our copper, it loses electrons and becomes more positively oxidized, so it's going to go through oxidation. Nitrogen goes from a +5 to a +4, so it becomes more negative or gains an electron. This means it is reduced. We see that the other form of nitrogen in the nitrate molecule on the product side did not change and remained a +5, and our hydrogen and oxygen molecules also did not change in this reaction. Our third step is to determine the changes in oxidation numbers. So, oxidized copper has increased by an oxidation number of 2, and reduced nitrogen has lessened or become more negative by an oxidation number of 1. Our next step is to change the oxidation to equal the magnitude adjusted by the coefficient of the equation. Because the changes in oxidation for nitrogen is a -1, we must add a coefficient of 2 to balance these nitrogens out and the +2 from our change in our copper atoms. This would apply to both our HNO3 and our NO2. Our equation should now read copper plus 2HNO3 yields CuNO3 plus 2NO2 plus H2O. Our last step of the equation is to use conventional methods to balance the remainder out. The coefficient of HNO3 must be increased from 2 to 4 to balance out the nitrogen atoms on the product side. This gives me copper plus 4 HNO3 yields copper nitrate plus 2 NO2s plus H2O. Now we have to account for our hydrogen, so we have to put a 2 on the water molecule on the product side so that we can get the balanced equation of Cu solid plus 4 HNO3 aqueous yields CuNO3 aqueous plus 2 NO2 gas plus 2 H2O. Okay, so that's one way to balance these types of equations. Now let's start talking about balancing half reactions. In chemistry, a species is any kind of chemical unit that is involved in a process. In the equilibrium equation of NH3 plus H2O at equilibrium yields NH4 plus 1 plus OH minus 1, there are 4 species. The first is NH3, the second is H2O, the third is NH4 plus 1, and the fourth is OH minus 1. Let's take a look at the reaction of 2Fe plus 3Cl2 yields 2FeCl3. If we isolate the oxidation portion of the reaction, we would see that iron would go from having a balanced electron shell on the reactant side to being iron plus 3 when it becomes iron 3 chloride. In other words, it lost 3 electrons. This gives us that Fe yields Fe plus 3. In order to balance this reaction out, we are going to have to add 3 electrons to the product side. We also need to represent the reduction portion of the equation by showing how chlorine gains an electron and becomes chlorine 1 minus. Since there are 2 chlorines in the product side of our reduction equation, this should read Cl2 yields 2 Cl minus. Now, in order to balance this out, or balance the 2 negative charges on our product side out, we will need to add 2 electrons to the reactant side. Now the reduction reaction should read Cl2 plus 2 electrons yields 2 Cl minus. Both the oxidation reduction portions of this reaction are considered half reactions. We can use half reactions to balance redox reactions by using the following steps. First, write the unbalanced net ionic equation for the reaction, omitting spectator ions. Second, write separate incomplete equations for the oxidation and reduction half reactions, including the oxidation numbers. Third, balance the atoms of the half reactions using electrons on either the reactant or product side. Fourth, adjust the coefficient so that the number of electrons lost in oxidation equal the number of electrons gained in reduction. Our fifth step is to add both half reactions together and reduce or cancel out like terms on both sides. Then our sixth and final step is to return our spectator ions, and if we want to restore these state of matter identifiers. Now let's work through these steps in the following redox reaction. FeS plus CuSO4 aqueous yields Cus plus FeSO4 3 aqueous. First step is to write the unbalanced net ionic equation and omit spectator ions. If we write the ionic equation for this, we would have Fe plus Cu plus 2 plus SO4 2 minus yields Cu plus 2 Fe3 plus 3 SO4 2 minus. We see that SO4 does not gain or lose electrons and has a negative 2 charge on both the reactant and product sides, so this means it is a spectator ion. This leaves us with our unbalanced net ionic equation of Fe plus Cu plus 2 yields Cu plus 2 Fe plus 3. Okay, so now we go to step 2. Step 2 has me writing out the half reaction for the oxidation and reducing atoms. So Fe is oxidized or gains electrons. So our equation for it would read Fe, whose oxidation is 0, yields 2 Fe plus 3, whose oxidation is plus 3. And our reduction half reaction would say Cu plus 2, whose oxidation, again, is plus 2, yields Cu, whose oxidation is 0. Our next step is to balance each reaction with electrons. We do this by adding 6 electrons to our oxidation reaction on the product side and adding 2 electrons to the reactant side of our reducing reaction. This way everything balances out. Our number of positive charges and negative charges equal out. Step 4 has me adjusting the coefficients so that the electrons cancel out. In order to get our 6 electrons to cancel out, we are going to have to multiply our 2 electrons and everything in that equation by 3. Now our reduction reaction should read 3 Cu plus 2 plus 6 electrons yields 3 copper atoms. Step 5 has me adding both these equations together and canceling out anything that is present on both sides. This would give me 2 Fe plus 3 Cu plus 3 yields 3 Cu plus 2 Fe plus 3. Our final step is to add our spectator ions and finish balancing out the equation. It should read 2 Fe solid plus 3 CuSO4 aqueous yields 3 Cu plus Fe2SO4 3 aqueous. Okay, the last thing we are going to have to go over today is to understand when to use which process of redox. The first question we're going to ask is, do the oxidation or reduction species appear more than once on either side of the equation? Or does the reaction occur in acidic or basic solutions? If the answer to those questions is yes, then we're going to use the half reaction method. If the answer is no, then we're going to have to use the oxidation number method to balance these redox reactions. Okay, the torture of balancing redox is over. Today you learned 2 methods for balancing redox reactions and when to use each of these methods. In saying that, keep up the good work in the class and see you next time.